Continuing with solving equations. Today we will discuss solving exponential equations. Now, what are exponential equations? Exponential equations are equations where the variable that we are solving is in the exponent. So when we have a power of a number, we have two parts that we are looking at. There is a base, and then there is the number at the top called the exponent, and the whole thing is called a power, right? And the number at the top is what tells us how many times we multiply the bottom number by itself. So if the number is 6, it means we take 6 of the bases and multiply them together, or 6 instances of that base and multiply them together. For example, 5 to the exponent 3 is 3 5s multiplied together, right? So that is what a power is. And in an exponential equation, the variable that we are solving will be in that position, right? Now, for you to be able to solve exponential equations, you need to first understand exponents, their definitions, and their laws. And then, in addition, you need to understand how to solve equations that are quadratic and that are linear. Now, for the linear equations and quadratic equations, we have videos that you can go through. So feel free to go to our videos on the page and also on our YouTube channel and check videos on solving equations, particularly focused on the quadratic and linear equations. Now, when it comes to the definitions and laws of exponents, I have them here alongside the space that I have here, and we can go through the definitions and exponents one by one just to refresh your memory. So, the definitions of exponents are 3 and the laws are 5. So let's go through the definitions. So we start with a and b, which will be our bases, that are real numbers, and n and m, that will be our exponents, which are integers. And here's how we define exponents, or here are the definitions for the exponents. Now, the first one tells us that if you have a raised to the exponent n, it means you have n a's and you're multiplying them together. So 5 to the exponent 2 means 2 5's multiplied together. 3 to the exponent 7 means 7 3's multiplied together. 10 to the exponent 15 means 15 10's multiplied together. The number of at the top tells us how many instances of the number at the bottom do we multiply together, or how many copies of the bottom number do we multiply together. That's the first definition. Now, the second definition is a to the exponent 0 is 1. It means that any number to the exponent 0 is 1. This means also even if you don't know the number, so if it's a variable, x to the exponent 0, the answer is 1. Y to the exponent 0, the exponent is 1. The answer is 1. Any number that is real to the exponent 0 is 1. Then the last one is the change of sign of the exponent definition. So this one tells us that you can change the sign of a power, of the exponent of a power. All you need to do is take the reciprocal after changing the sign of that exponent. So if you have a to the exponent negative 2, you want to change it to positive. Change it to positive, and then from there, take the reciprocal of it. Then these two are equal. If you have, if we come back here, 2 to the negative 3, and you want to change it to a positive exponent, you will first change it to the exponent and then put 1 on top. So that gives us a way of working with positive exponent even when we have negative exponent, or a way of working with negative exponent when we have positive exponents. So simplifying this, we would have gotten then 2 times 2 times 2, which is 8. But that is just an example. So the last definition allows us to change the exponent of any given power to be either positive or negative. So it's the change of the sign of the exponent definition. Right. Then let's go to the laws. We have 5 laws. Now I like to group them into 3 groups. So the ones related to same bases, I call them same base laws. And then the ones related to what? The same exponents but different bases, so I call them same exponent laws. And lastly, the one that says you take a power of a power. In other words, you raise a power to a different exponent, or it's the same or a different exponent. In other words, taking a power of a power. So let's start with the same exponent laws. What do they say to us? So the first one says if you multiply powers with the same bases, you can simplify this by just taking one base and then adding the exponents. The second one says if you take powers with the same bases and divide them together, then you can subtract the exponents to simplify. Depending on whether you want the answer to be a negative exponent or a positive exponent, you either take the top exponent and minus it in the bottom, or the bottom exponent and minus it in the top. So, for example, if you have 2 to the exponent 7 times 2 to the exponent 3, this will be 2 to the exponent 7 plus 3, which is 2 to the exponent 10. And if you have 3 to the exponent 11 divided by 3 to the exponent 5. If you want the exponent that is positive, you'll take the top one minus the bottom exponent. So you take one base, subtract 11 by 5, and you get what? 3 to the exponent 6. But if you want a negative exponent, then you will say 3 to the exponent 5 minus 11, which gives you, you will put the 1 on top. When you do that, because the 3 is in the bottom, you put 1 on top and say 3 to the exponent 5 minus 1. And this gives you 1 over 3 to the exponent negative 6. And if you look at this, and you look at that, and you look at that definition there at the top, the change of exponents, the change of the sign of the exponent, you can see that they agree. So here the sign is different from the sign there, but this one has a 1 on top, this one doesn't have a 1 on top. So that is how you would do same base laws. We can do it with variables, but with variable powers, but that's not necessary at this point. Then let's go to the second set of laws, the same exponent laws. So let's say, for example, you have 2 to the exponent 3 times 5 to the exponent 3. So if you have 2 to the exponent 3 times 5 to the exponent 3, what the first same exponent law says is that you're multiplying 2 powers with different bases but same exponents. You can just multiply the bases together and keep the exponent. What this says is that we can take the 2 multiplied by the 5, then we get 2 times 5 and to the exponent 3, and this is 10 to the exponent 3. So you can do that. Then the second law says if you have different bases, let's say you have 8 to the exponent 3 over 4 to the exponent 3. It says that if you are dividing powers with different bases but same exponents, you can divide the bases together. So you can just say 8 divided by 4 and then you keep the same exponent. And this becomes 2 to the exponent 3, which if you want to write the value of, then it becomes 8 because it's 3 2's multiplied together, which is 2 times 2 is 4 times 2 is 8. Okay, so that is the second set, which is same exponent laws. And then the last one says that if you have a power and you take another power of it, then to simplify this, you can actually say you have 2 to the exponent 3, for example, and you take to the exponent 4. Then all you need to do is to simplify this is just take the exponents and multiply them together. This gives you 2 to the exponent 12. if you want to check if this is making any sense, you can also take this and apply the first definition, which says that a to the exponent n is n a's multiplied together. In this case, our a will be the inner power. So that means when we have 2 to the exponent 3 all to the exponent 4, which we worked out with the power of a power rule to be 2 to the exponent 12. If we do it with the first definition, it will be 4 of copies of 2 to the exponent 3 multiplied together. So if we don't want to use power of a power, and we just want to check if it makes sense, we can do this. This is by definition 1. 4 copies of this multiplied together. But now with this, we see that, wait, all the bases are the same, so we can apply the first same base law, which says when you multiply, you can add the exponents. And clearly, we're going to have 3 plus 3 plus 3 plus 3, which is 2 to the exponent 12 again. So the laws cannot contradict each other at all in the definitions, because they were created or crafted carefully. All right, so now that we have gone through the definitions and laws of exponents, we are ready to solve for x in exponential equations, or to solve exponential equations. Right, so let's go back to exponential equations. We said an exponential equation is an equation that involves the variable in the exponent. And at the top here, we have examples of exponential equations. If you check in all of them, the exponents, the variables are in the exponential area, or in the place where the exponent is. So how do we solve exponential equations? So we mainly depend on our knowledge of factorization and also prime factorization of numbers. So there are videos that we've done of factorization and then also solve for x, right? But the factorization that is most important here in simplifying the problems is prime factorization. Once you know prime factorization, then you can be able to transform any base to prime numbers. And this is a very useful skill in solving exponential equations. Then again, knowing how to solve for x in quadratic and linear equations is also very important. Right, so what are the main tricks that we normally use in order to solve these problems? The biggest trick here is to have 2 powers with the same basis but different exponents. Right, with that, we argue that because these 2 powers are equal and they have the same basis, then their exponents must be equal. So this means that x is equals to y, or y is equals to x. Another possibility here is if we have a to the exponent x and b to the exponent x. We argue again, or let's say what? Yeah, if these powers are equal and their exponents are equal but the bases are not the same, then we know that a must be equal to b. But I need to rephrase this. Maybe it's nicer if we put it like this. If we say x to the exponent a and y to the exponent a, we argue that we have, well, 2 powers here where the bases are not the same. In fact, they are unknown, right? And the exponents are the same. Then it means that whatever is here is equals to there. So those are the kind of arguments that you have, right? But in most cases, we will be dealing with this one. Now, let's solve for, now we will go on and solve the examples that are given. Okay, so when solving exponential equations, we will use the argument that if two powers are the same and have same bases, then their exponents are equal. Or if two powers are equal and their exponents are equal, then the bases should be equal. The most important is the first one. So let's see. The first equation, 2 to the exponent x plus 5 is equals to 32. How do we do that? Now, we will need to first make sure that all our bases are prime numbers when we are solving exponential equations. So in this case, we have a power here of 2, and on the other side we have 32. We check, can't we make this also to have a base of 2? Well, we can, and this is where prime factorization comes in. With prime factorization, we divide by the same prime number until we can't divide with it anymore. Any prime number that doesn't divide perfectly, we skip it. It's not a factor. So we start with the first prime number, which is 2, and increase on and on. Once 2 can't go anymore, we go to 3. Once 3 can't go, we go to 5, and so on. So 32 divided by 2 is 16. We can still divide by 2. So 16 divided by 2 is 8. We can still divide by 2. 8 divided by 2 is 4. Divide by 2 is 2. Divide by 2 is 1. So this is called the ladder method. Right. It's like a step ladder. So you're going down the rungs. So now this gives us the prime factors of this. So with this, then you get what? The right hand side will then become 2 to the exponent 5. And so we have what? Powers that are equal and have the same basis. So that means that their exponents are equal. Now with this is a linear equation because the highest exponent is 1. Right, so that means we can take the 5 to the other side because when solving a linear equation, remember, constants to one side and variables to the other side. So 5 to the other side becomes 5 minus 5, and so the answer is 0. Therefore, x is equals to 0. And then you can check if this is making sense by substituting back into the equation. So the left hand side will be equal to 2 to the exponent 0 plus 5, which is 2 to the exponent 5, which is 32. Right. So that means that this is equal to the right hand side as well. So there we go. We have solved the first one. Right. Going to the second one. We're going to need some space because we're using the ladder method to prime factorize. Let's say I have 64 to the exponent y plus 1 is equals to 16 to the exponent y plus 5. So in order for us to simplify this, the easiest way is to prime factorize the bases. We see that, wait, all of this, we can factorize them. So why don't we factorize them first and see their prime factorizations and then decide what to do from there. So we do exactly that. 64, prime factorize it. Remember, start with the smallest prime number and you divide. Once it can't divide anymore, you go to the next one and so on. 64 divided by 2 is 32. We already did the prime factorization for 32 and we know it's going to be what? 16, 8, 4, 2, 1. So then the 16 one we can see it from here. So we don't have to do it from scratch. So that means on the left hand side we basically have 1, 2, 3, 4, 5, 6. 6 copies of 2 multiplied together. So we have 2 to the exponent 6 plus 1 is equals to, and then for 16 we have 4. 2 to the exponent 4. So 4 copies of 2 multiplied together plus 5. Now with that we have what? The bases are the same. And also notice that we have a power of a power here as well. So that means that we are going to multiply the exponents to simplify. But we already know that the exponents should then be equal because these are powers that are equal because of the equal sign there, and they have the same basis. So we're going to multiply and equate the exponents here. So that means we have this equation. And with this equation, we can see it is linear again. The exponents are all 1. So what do? We simplify, then take variables to one side, constants to the other side. So what do we have? 6y plus 6, 8y plus 20. Variables to one side, take 6y to the other side and 20 to this side, you get 6 minus 20. Remember, when you transpose, the term will change the sign. So we're going to have 6 minus 20, which gives us minus 14. When you take 6y to the other side, we get 8y minus 6y. When you transpose, you change the sign of the term that is being transposed. So we get what? 8 minus 6 is 2. So 2y. And then to finish, you divide by the variable of the, we divide by the coefficient of the variable on both sides. So now that means we have what? Y is equals to negative 7. And if you want to check if this is correct, you can do the left-hand side. This is the last one where we will check. The rest we'll just start doing them then. 64 to the exponent negative 7 plus 1 is equals to 64 to the exponent negative 6. The right-hand side is equals to what? 16 to the exponent 2 into negative 7 plus 5. This is going to be negative 14 plus 5 is 16 to the exponent negative 9. Now, if you press the calculator, you will see that the answers are the same, but I'm not going to do that. Right. So that means that y is equals to negative 7 is the solution. Now, let's go to the next one. We have negative half of 6 to the exponent m over 2 plus 3 is equals to negative 18. Now, remember, to simplify an equation, you can do anything you want as long as you do it on both sides the same way. So, we're going to start by removing the negative. Multiply both sides by negative 1, but also we want to remove the half so that we have only this base here, this power alone. So we're going to multiply by the reciprocal of half, which is what? 2. And since there's negative, we're going to multiply by negative 2. So multiplying by negative 2 on both sides. Negative 2 times negative half is going to be 1. And if it's a 1, we don't write it. So here we're going to be left with 6 to the exponent. So negative half here, multiplied by negative 2 is equals to negative 2 multiplied by negative 18. And so these two are reciprocals of each other, so they'll give us 1. So we're left with 6 m over 2 plus 3 equals 36. 36. Now, in this case, you can prime factorize. But if you can express the number on the other side in terms of 6 as well, you might as well do that. So we have two options. We can prime factorize both bases, or we can express this base here in terms of the base on the other side. We know 36 is 6 times 6. So we can just write this as 6 squared. If we do that, then we're going to have m over 2 plus 3 is equals to 2, because our argument is the powers are equal and they have the same basis. So that means their exponents must be equal, because otherwise then these powers can't be equal and have different exponents while they have the same basis. Right. Then with this, we know it's a linear equation because the exponents of the variables are all equal to 1. In fact, there's only one variable. Take the 3 to the other side, what do we have? M over 2 is equals to negative 1. Then we want to get rid of the 2. And this 2 is dividing the m. So we need to multiply by 2. So what do we do? 2 times m over 2 is equals to 2 times negative 1. And what do we have? M is equals to negative 2. As I said, I'm not going to check the answers anymore. But if you want to check the answer, you could just put the negative 2 where the m is. And so by inspection there, we're going to get negative 1. Negative 2 divided by 2 is negative 1. Plus 3 is going to be positive 2. So 6 squared is going to be 36. Multiplied by negative half is going to be negative 18. So this is then correct. Alright. But let's say you didn't want to do it like this. Let's say you just started by prime factorizing. So you are going to have 6 divided by 2 is 3, divided by 3 is 1. You're going to have 36 is divided by 2 is 18. Remember, you divide by the same prime number until you can't divide anymore. Then you skip to the next one. And then you skip any ones that leave remainders. So we can divide by 2 again, we get 9. We can't divide by 2, divide by 3 now. Divide by 3 again, you get 1. So what you were going to have here was going to be 2 to the exponent 2 times 3, sorry, to the exponent m over 2 plus 3 is equals to, here we're going to have 2 squared times 3 squared to the exponent what? Just 1. Okay, there's no exponent there, so it's 1. Then this was going to be 2 times 3 is 6 again. So it was going to take you to 6 again over 2 plus 3. And this was going to be, we have same exponents. When we have same exponents and we multiply, we can multiply the bases and keep the exponents. So we're going to have what? 2 times 3 to the exponent 2. And this gives you what? 6 over 2 plus 3 is equals to 6 to the exponent 2. And so again, the bases are the same. But this is a long try now. Sometimes you must just check the base that you have on this side is not related to the number that you have on the other. Sometimes it is, and most of the time it will be squares or cubes. Right, so check that first. But if all else fails, just revert back to prime factorizing. That really makes the work very easy. Now let's go to the next one. The next one is 2 times 2 to the exponent x minus 16 into 3 to the exponent x plus 1 minus 9 equals 0. Now, let's look at this carefully. If you remember when we were talking about solve for x, we said that if you multiply factors and you get 0, or if you have multiply any two numbers that are unknown and you get 0, it means one of them is 0 or all of them are 0. At least one of them must be 0, because any number multiplied by 0 will be 0. So if one of them is 0, then the answer will be 0. If all of them are 0, the answer will be 0. Or if any number of them is 0, then the answer will still be 0. But one of them at least has to be 0. So here we have this bracket multiplied by this bracket and we get 0. That means that we can simplify this by saying what? This first bracket either is equal to 0 or the second bracket is equal to 0. I mean, there's no way we can multiply two things and get 0 and one of them is not 0. That's not possible. Any number multiplied by 0 is 0. So if you multiply these two and get 0, either the first one is 0 or the second one is 0. And this is what helps us to simplify any equation after factorizing. We separate the factors by using this argument that, well, they can't give us 0 when we multiply them unless one of them is 0 or all of them are equal to 0. So now, by doing that, then we have simplified this. Okay. So what do we have? 2 times 2 to the exponent x. We have two terms basically. We can take this to the other side and then try to use that equal powers argument. So taking negative 16 to the other side becomes 16, or 3 to the exponent x plus 1 is equals, take the 9 to the other side, you get positive 9 from negative 9. Remember, when you transpose, you change the sign of the term that you're transposing. Now here we are having simpler equations now than the original one. So what we do from here, we see no, but this is not, this is disturbing us. All right. So we want the power by itself, not multiplied by anything. So what we're going to do is divide both sides by 2. Divide by 2, divides there, and this one goes in here 8 times. So we're going to have 2 to the exponent x is equals to 8. So on this, in this case, it's very easy to know what the power will be. In fact, 2 times 2 times 2 we know is 8. If you don't know, now you know. 2 times 2 times 2 is 2 to the exponent 3. So 8 is always equal to 2 to the exponent 3. It's also coming from cube numbers. Now on the second one, we have what? 3 to the exponent x plus 1. Like I said, whenever you have a base here and a base there, try to check if you can express the second number there or the other number in terms of the base that you have on the power. And in this case, we can. 9 is 3 squared. And so here we get what? In the first one, we get x is equals to 3 because we see powers that are equal and having the same basis, then the exponents should be equal. All x plus 1 is equals to 2 because the powers are equal but the bases are the same, and so the exponents should be the same. Now this gives us what? Again, is a linear equation. Take the 1 to the other side and you get 2 minus 1, which is 1. Again, I'm not going to check. You can check. You could just substitute the values. Substitute x is equals to 3 here, 3 there, and see if you get 0. And then substitute 1 there, and see if you get 0. You can do it by inspection. 2 to the exponent 3 will be 8 times 2 is 16, minus 16 is 0. If we put 3 here, we get 4. 3 to the exponent 4 is 81, but already this is 0. So multiplying 81 minus 9 with the 0 will give us 0. So this works. If you have x is equals to 1, if you put it here, you get 2 to the exponent 1, which is 2, and 2 times 2 is 4, minus 16 is negative 12. But if you put the 1 here, you get 3 to the exponent 1 plus 1, which is 3 to the exponent 2, minus, which is 9. Minus 9 is 0. So even though you have negative 12 here, here you have 0. So again, negative 12 times 0 is 0. So the answers are both correct. Right, so the solution is x equals 3 or x equals 1. Then let's go to the last two. Now, on the last one, we have 2 to the the second last, we have 2 to the exponent a equals 0.1, 2, 5. Now, when doing exponential equations, when you meet a question like this, you must remember that you can change this to a common fraction. And to change this to a common fraction, all you do is count how many decimals are there. Right. So you will remove the decimal point and you'll have 1, 2, 5. If it wasn't 0, you would put also the number that is before the decimal point there. Then you divide by 1 followed by 3 zeros. In other words, 1,000. If it was 4 digits, we would divide by 10,000 because it will be 1 followed by 4 zeros and so on. Now with this, you can simplify now. You're going to have 2 to the exponent a is equals to, let's find common factors here. 125 goes into itself once. 125 and 125 give us 250. And that means we've counted 125 twice. 250 goes into 1000 4 times. But each 250 represents 2 125. So that means that 125 goes 8 times into 1000. So that means we have 1 over 8 here. But now, remember, 8 is 2 to the exponent 3. So we have 1 over 2 to the exponent 3. But now this doesn't look nice because here we don't have this in the denominator. But here we have the power of 2 in the denominator. Now this is where we apply this definition. We want to remove the power from the denominator in this case. So we have to change its sign. Or we can put this in the denominator. So we'll put 1 on top of it, but we have to change the sign. So whichever side we change, we must change the sign of the exponent. So we're going to say 2 to the exponent a, and then remove this from the denominator, but then change the sign of the exponent. So when you change the sign of the exponent, you must remove the number from the denominator or put it in the denominator, depending on where it is before you change it. Right, now we have powers that are equal but having different, they are equal but and also have same bases. So that means that their exponents should be equal. So our answer is a is negative 3. So if you want to check this gives us what? 2. This one I'll check it manually. 2 to the exponent a becomes 2 to the exponent negative 3. And 2 to the exponent negative 3, according to this definition, is the same as 1 over 2 to the exponent 3, which is the same as 1 over 8. And this, if you do it with long division, 1 divided by 8 is not, because 8 doesn't go into 1. Once you put the naught, you put comma, and you put a 0. 8 into 10 goes once and leaves a 2. Right. Now, 8 into 2 doesn't go. So we move to the next digit. You put a 0, it goes twice, and it leaves a 6. 8 doesn't go into 6, so we go to the next digit. We put a 0. 8 into 60 goes 5 times. Does it go 5 times? Sorry, I made a mistake here. This leaves 4, and then we have 40. 8 in here goes 5 times. I made a mistake there, so I already know the answer is not 125. Just made a mistake there. If you minus 2 8s in here, 16, you get the remainder of 4. And so that's it. So that means this is equal to 0.125. And so the solution is actually correct. All right, let's go to the last one. On the last one, we have 2 times 5 to the exponent 2 minus x is equals to 5 plus 5 to the exponent x. Now, in order for us to solve this one, we note that this exponent is positive, this one is negative. Well, maybe we should change this one to be positive as well, so that we have exponents with the same signs. And if we remember, if you want to change the sign of an exponent, you have to change it, if it is not in the denominator, to the denominator. If it is in the denominator, to the out of the denominator or to the numerator. So here we're going to have what? 2 times 5 to the exponent 2 divided by 5 to the exponent positive x. Because we wanted to change the sign of it, we took it to the bottom. In fact, this is again also just like the division law that you have here. If you have a to the exponent n minus something, that something must have been in the bottom maybe. You see. Alright, so that's what you have. But I have applied the first definition to get there. To change the sign of this, you take it to the bottom since it's not in the bottom already. Okay, now we have what? 5 plus 5 to the exponent x. And now, since we have 5 to the exponent x in the bottom and we don't want to have numerators here, denominators generally, we'll multiply by 5 to the exponent x on all sides. Multiplying by 5 to the exponent x, here we're going to have what? 2, because the 5 to the exponent x will cancel this one. And then